Dear students, in this lecture, we will be going to solve a numerical problem on design of RCC beam, which is subjected to torsional moment. That means the beam section, which will be subjected to torsional moment along with bending moment, flexure moment, as well as shear. Now let us go through the statement. Design the torsional reinforcement in a rectangular beam section 350 mm wide by 750 mm deep, which is subjected to an ultimate twisting moment of 150 kilonewton meter combined with an ultimate hogging moment of 200 kilonewton meter and an ultimate shear of 120 kilonewton. We can take M25 grade of concrete and Fe 415 steel, as well as this beam will be subjected to mild exposure conditions. So here very important part is the flexural movement is given as ultimate hogging movement. That means it is given in the statement itself that it is a negative movement. So we can assume that the section which we are going to design that may be located at the support or at the fixed end, and it is subjected to torsional movement. So that's why bending movement either at a fixed end or at a support, fixed support, it may be negative bending moment. So that we have to keep in mind. That is a very important part of this numerical. Now data available, it is clear that it is a rectangular beam. Dimensions are given. B width is 350 millimeter. Overall depth is 750 millimeter. M25 grade we can assume if we take M25 grade concrete, then FCK will be 25 MPa. And if we take higher grade, then accordingly we will revise the guidelines. That means FCK value will be taken care of. Fe 415 steel, that means yield strength of the steel will be 415 MPa. Now loads or the moments which are given in the statement. First of all, it is given that ultimate twisting moment. So TU is ultimate twisting moment, that is 150 kilonewton meter. Mu is the ultimate bending moment. Here in this case, it is hogging 200 kilonewton meter, and ultimate shear force 120 kilonewton. Now, since it is the condition of mild exposure, that means beam, after construction, it will be subjected to mild exposure conditions. It is exposed to mild exposure conditions. So, minimum cover to stirrup required is 20 millimeter at least, as per IS 456. And let us assume the effective cover as 50 millimeter all around. That means all sides of the beam cover to the effective cover to the reinforcement is 50 millimeter. So due to that, the effective depth of the section will be 750 minus 50, that is 700 millimeter. Now the main part of the problem is we have to design the torsional reinforcement since it is subjected to torsional movement. So in reference to the clause number 41.4, which we have discussed in detail in the previous lecture, longitudinal reinforcement, we have to provide longitudinal reinforcement as well as transverse reinforcement. So first of all, let us discuss about the longitudinal reinforcement. The longitudinal reinforcement need to be designed to resist equivalent bending moment. That is ME1. ME1 is the equivalent moment as mentioned by the or recommended by the IS 456. That means what we are doing, we are converting ultimate twisting moment and bending moment combined, and they will give the ultimate equivalent bending moment. So equivalent bending moment, that is MT plus MU. ME1, MT is the given by this formula that is available in IS 456. That is MT is equal to TU into 1 plus capital D by B divided by 1.7. So by putting all the values, we are getting MT, that is the twisting moment, you can say. That means torsional movement is converted into movement. So this comes out to be 277.3 kilonewton. And after that, we can easily calculate ME1, that is the equivalent bending moment. for which we need to design the reinforcement. So MT plus MU comes out to be 477.3 kilonewton meter. So here we can refer the guideline mentioned in clause number 41.4.2.1, which is relevant to this type of a numerical problem. So referring this clause, there is one guideline, one condition, that means if MT is greater than MU, even in this case, here MT is coming out to be 277 and MU is 200. So ultimately, this condition is valid here. Then what we have to do, we have to design the longitudinal steel need to be provided. For ME1 here 477.3 kilonewton meter on flexural tension at top face. Why flexural tension? Because it is a hogging movement, so tension will be at the top fiber and compression will be at the bottom fiber. If this was the sagging movement, that means it was positive bending movement, then we have to design in the other sense. That means the reinforcement required to take care of ME1, that will be taken in the flexural compression zone. So accordingly we have to decide, and additional longitudinal reinforcement that will be equal to ME2 is equal to MT minus MU. That means because MT is greater than MU, so we are subtracting and we are getting the balance bending moment, and that balance bending moment need to be taken into consideration for designing the additional steel, and this additional steel will need to be provided on the flexural compression. So in this particular numerical, at the top is flexural tension and at the bottom there is flexural compression. Now carrying forward this numerical, so MT we have calculated 277.3 and ME1 we have already calculated, that is 477.3 kilonewton meter, and ME2 is 77.3 kilonewton meter, that is the balance movement. Now again same guideline which we have already discussed. That means now first of all let us design longitudinal reinforcement which we have to provide on the top face. That means we have to provide this reinforcement, we have to provide for taking care of this movement ME1. So ME1 is 477.3 kilonewton meter. Now here we are referring SP16. So ready-made, these are SP16 special publication which are very helpful in the designing, and it make the design problem very easy. So SP16 1980 version we are going to refer here. So this is the snapshot of the SP16. Now this table 3 is applicable for the current problem since FCK is 25, so 25 Newton per millimeter square. Reinforcement percentage here we can calculate for singly reinforced section. So here this table number 3 will be giving us the percentage of steel PT. So this table is applicable for M25 grade of concrete, so SP16 1980. So for getting the value of a percentage of steel, we need two values. One is MU by BD square, and that is second one is the FY value, that is yield strength of the steel which we are going to use. Now in current problem, ME1 by BD square we are calculating. ME1 is 477.3 into 10 raised to power 6. So by making it into Newton millimeter, and divided by BD square, width of the beam is 350 and effective depth of the section is 700. So ultimately we are getting this factor ME1 by BD square, that is equal to 2.783, and FY is 415 and FCK is 25. So from this table corresponding to MU by BD square value 2.783 and FY 415. So 2.783 value lies between these two values, that is 2.75 and 2.8, and correspondingly two values which we have to take into consideration, that is 0.896 and 0.916. So by doing the interpolation, with the help of interpolation, we can find what is the percentage of steel value, that is percentage of steel required for MUY square value 2.783. So after doing the interpolation, we are getting the value percentage of steel required PT is equal to 0.91. So correspondingly, we can find out the area of steel required, since PT can be taken as equal to area of steel divided by 100 percentage of steel. This is you have to keep in mind that PT is percentage of steel. So area of steel we have to calculate, that is 0.91 divided by 100, since it is a percentage of steel, into B and D, width of the section and effective depth of the section. So based on these calculation, what we get, that area of steel required to take care of this much bending moment, or equivalent bending moment we can say. So area of steel required is 2230 millimeter square. So accordingly, we are going to provide 4 number of 28 dia bar at top flexural face. That is, and when we provide 4 into 4 bars of 28 dia, then area of steel provided will be 2461. So in the previous slide, we have find out the longitudinal steel which was required at the top face. So now here in this step, we are going to calculate longitudinal steel which need to be provided at the bottom face. Again, we are using the SP16 table ME2. So this was the movement which for which we need to design the bottom reinforcement. So ME2 comes out to be 77.3 kilonewton meter. So accordingly, as we have done in the previous step, we can refer SP16, and with the help of this table, we can work out what is the area of steel required, percentage of steel required. So ME1, here we have to write ME2. There is made one correction, ME2 by BT square. So it comes out to be 0.45. So based on the value of 0.45, we can directly pick the value from the table, and that value based on 0.45, and this is 0.127. So percentage of steel required to take care of Me2, that is equal to 77.3 kilonewton meter. Percentage of steel comes out to be 0.127. So many of students were asking that whenever we are making the video solving the numerical, then we should use some language, that means moderation in the language English as well as Hindi. So in the next video, we will be trying to elaborate the information in Hindi as well as English. So required area of steel based on this percentage of steel 0.127. So we have calculated. So 312 millimeter square area is required, which we have to provide at the bottom face. Now, since this area of steel required comes out to be very bigger quantity, very lesser quantity. So here we are making a caution here, that means what is the codal recommendation for minimum area of steel. So based on the formula in the IS 456, so we are going to calculate what is the minimum area of steel required, or recommended by the IS 456. So minimum area of steel as recommended by IS 456 comes out to be 513. So we will not provide 312, rather we will provide minimum area of steel. So for this, we have decided to provide 3 number of 16 mm dia bar at the bottom flexural face, and correspondingly the area of steel provided value comes out to be 602 millimeter square. Now in this step, we are going to provide the side face reinforcement. Now what code gives? Code suggests that in clause number 26.5.1.7, that longitudinal steel shall be placed as close as is practicable to the corner of the cross section, and in all cases there shall be at least one longitudinal bar in each corner of the tie. So this condition we are fulfilling. Now very important part of this clause is when the cross section dimension of the beam exceed 450 mm. That means when the depth of the beam increase is more than 450 mm, that is in the case of torsional movement, then we have to provide the side face reinforcement as per the guideline given in 26.5.1.3. So you must keep in mind here that if your beam which you are going to design is not subject to torsion, then side face reinforcement will be required when the depth of the section is beyond or exceeds 750 mm. But when we are talking about the beam to be designed to take care of torsional moment, then that limit is 450 millimeter. So referring this clause 26.5.1.7 and 26.5.1.3. Now this clause, as we have discussed, since depth of the section is more than 450 mm, so we need to provide the side face reinforcement. And as per this clause 26.5.1.3, the minimum area of steel which need to be provided as a side face reinforcement, that should be 0.1% of the gross section of the gross area of the section. So 0.1% of 350 and into 750, so it comes out to be 263 millimeter square. So what we have decided to provide 4 number of 10 mm dia bar, which will give 452 millimeter square. So 2 bar on each side face we are going to provide, with vertical spacing between longitudinal bar not less than 300 millimeters. So these are the guidelines which are recommended and provided in clause number 26.5.1.3. So next part is we are going to design the transverse reinforcement. And transverse reinforcement, to provide transverse reinforcement, we need to refer the clause number 41.4.3. So for this, first of all, we have to calculate the equivalent shear force, as we have done in the previous steps, equivalent bending moment. So here we have to calculate equivalent shear force, and in reference to caudal advice, we need to calculate equivalent shear force by using this particular formula, and putting all the value, we are getting this equivalent shear force is equal to 805.714 kilonewton. And accordingly we can calculate equivalent nominal shear stress. So but in this step it was force, now we have to calculate tau value, that is shear stress. So tau VE, that means shear stress, equivalent shear stress is equal to VE upon VD. So after doing all the calculation, we are getting tau VE is equal to 3.288 MPa. Now as per caudal guideline, here we this much shear stress is coming on the section, or we can say the section is exposed to this much shear stress. Now first of all, we have to apply the check whether the concrete section, what is the optimum or what is the maximum shear strength carrying capacity of the section. So maximum shear stress, that is tau C max, you can refer it for M25 grade of concrete and Fe 415 steel, and this value we can get from table number 20. Table number 20 ISO 456. So this value comes out to be 3.1 MPa. Now you can compare here tau C max, which is allowed by the code. That means what is the maximum limit of the shear strength carrying capacity of the concrete section? It comes out to be 3.1, but the section is subjected to shear stress, that is 3.28, which is higher than this value. So this is the step which we need to have taken into consideration, that tau VE is greater than tau C max. So that means we can't go when this condition is occurring. So the section need to be redesigned, because tau V is increasing the maximum limit of the shear stress carrying capacity of the section. So now how we can redesign? Either we can take a higher grade of concrete or we can change the section size. So more predominantly, since the section size is already given, and if the section size cannot be changed, then we have only one option, that means we need to increase the grade of concrete. So here we have tried to keep the same section dimensions, and we have increased the grade of concrete to M30. Earlier it was taken M25, now we have increased it up to M30. So for this N30, what we have to do, we have to do the all the calculations. So we have to revise the calculation. So this was the earlier step which we have taken. Now for M30 grade of concrete and Fe 415 steel, tau C max value comes out to be 3.5. Now you can see that this value is greater than uh, tau VE. So it's okay. So tau C max is greater than tau V. So we can design the transverse reinforcement. Now another step is, first of all, we have to calculate the percentage of steel provided. So it comes out to 0.91. And from table number 19, now we will refer table number 19. And from that table number 19, we are getting the value of tau C. So tau C comes out to be 0.63. And let us assume that we will be providing 12 mm dia, 2 leg stirrups. So for one stirrup, the area ASV comes out to be 226 millimeter square. Now we can refer this diagram very carefully. So overall dimensions of the section is 750 by 350, and 50 mm effective cover we have taken from all sides. So from top, from bottom, etc. So 4 number of 28 mm dia bar which we have designed, that is longitudinal reinforcement, we are provided at the top level, and 3 number of bars of 16 mm dia we have provided at the bottom level. Now we are going to design the shear stirrups. So 12 mm dia stirrup we are going to provide. So this spacing we are going to calculate now. So SV is the required spacing. So first of all, we can use this formula. And this is the rearrangement of the formula from the IS code. So by putting all the values here, D1, B1, etc. So now B1 is the center to center distance between the corner bars along the width of the section. And D1 is the center to center distance from the corner bars along the depth side. So this D1 we can calculate 650, and B1 comes out to be 250. So by putting the value of B1 and D1 here, we are getting that SV required is 81.84 millimeter. Now here you have to note down this another point. This is the formula which is given in IS 456. So based on this formula, we have to calculate the spacing. So for this formula, spacing comes out to be 0.87 FYASB divided by tau VE minus tau C into B. So putting the values here, we are getting SV should not be greater than, should be less than or equal to 89.73. And another equation which code is suggesting that SV should follow this guideline also, that is X1. Now what is X1? X1 is the center to center distance between the these shear stirrups along width side, and Y1 is along the depth side. So X1 we have calculated, that it comes out to be 278. Another condition is X1 plus Y1 by 4, that is 229, and 300. After that, what we are getting, based on all these calculations, we have decided that what is the minimum value of shear spacing of the shear stirrups, that is required 81.84. So we have decided to provide 12 mm dia bars of 2 leg stirrup at 80 mm center to center. And this is the whole solution of the numerical whenever there is a beam section, and that beam section which is subjected to torsional moment. Now from this diagram, everything we have discussed, only one part is pending, that is the side face reinforcement. So we have provided 2 bar along one side and 2 bar along the second face. So 4 number of 10 mm dia bar we have provided. Thank you.